Hi friends, welcome to this video on application of Laplace for solving a differential equation. Engineering is a field which is almost filled with differential equation at each and every point of time, and solving it can be done using various techniques. Laplace is going to be one of the two for solving a differential equation which arises more frequently in an engineering field. The differential equation can be classified as ordinary differential equation and a partial differential equation. This video is going to help you solve an ordinary differential equation using the Laplace technique. So first, what are going to be the requirements for it? When I am going to solve a differential equation using Laplace, I need to know what is going to be the Laplace of the derivative. So because it is a differential equation, so it involves derivatives. In general, we have Laplace of y power n of t as s power n Laplace of y of t minus s power n minus 1 y of 0 minus s power n minus 2 y dash of 0 minus s power n minus 3 y double dash of 0 and so on. We notice that when the power of the derivative is going to be n, I have s power n minus 1, n minus 2, n minus 3 and so on. Starting with n, the power of n is diminishing. And now look into the derivative Laplace of y of t. And next I have y of 0, y dash of 0, y double dash of 0, y triple dash of 0 and so on. The derivative increases. S diminishes, y increases or the derivative increases. So if you are going to consider this with first term alone positive and negative sign everywhere, then it becomes easy for us to memorize this formula. In general, the problems which we are going to solve will be involving the first and the second derivatives in general. So let us first try memorizing these two formulae for the application of Laplace to solve differential equation. So we have the first derivative Laplace of y dash of t as s Laplace of y of t minus y of 0. Apart from the first term, remaining all the terms are going to be negative. Laplace of y double dash of t is s square. Laplace of y of t minus s y of 0 minus y dash of 0. Just if you will generalize formula is memorized and you put n as 1 and n as 2, you will be getting the first two formula. Better you memorize the first and the second formula individually, then we will be easily solving the differential equation using Laplace technique. Come on, we will try to solve the differential equation y double dash minus 3y dash plus 2y equal to e power t given y of 0 is 1 and y dash of 0 equal to 0. I have a second derivative and I have a first derivative. So what will be the formulas required for this will be Laplace of y dash of t and Laplace of y double dash of t. The technique for solving is, as such we have a differential equation. So what we are going to do first is apply Laplace on both sides. So when I apply Laplace on both sides, I will have Laplace of y double dash of t minus 3 Laplace of y dash of t plus 2 times Laplace of y of t to be equal to Laplace of e power minus t. Now I will try to solve this Laplace, get a answer for it. Now we have introduced a Laplace. So to get or retrieve the solution back, I will have to apply inverse Laplace. So the technique is first step apply Laplace and in the last step apply inverse Laplace. So what you will be ultimately getting is the solution for the differential equation, which is nothing but your y of t. So keep in mind the ultimate aim is to find what is my y of t. So to aid in the solving, we have been given two conditions. Y of 0 is 1 and y dash of 0 equal to 0. It is estimated at t. So what is the value of t here? 0, and this value of t is 0. Since it is estimated at t equal to 0, these two conditions are referred by the name initial conditions. So this initial conditions will help us solve the differential equation. In general, when you solve a differential equation, you will be getting a complementary function, a particular integral, and then you combine both of them to get your general solution. But when you apply the Laplace technique, we will be directly getting the final answer. Now, these conditions will help us to evaluate the values of the arbitrary constants A and B involved in the equation. So, this Laplace is going to be a tool which gives me directly the final answer rather than going step by step. Hence, it makes the problem much simple for me. So now let us try evaluating this Laplace using the given condition. Now as such, what we have done? We have applied Laplace transforms on both sides of my differential equation. So this is what I get. Now I can resubstitute for this Laplace of y double dash of t from over here, which gives me s square Laplace of y of t minus s y of 0 minus y dash of 0. So I have replaced my Laplace of y double dash of t with this formula. What is the second thing given to me? Laplace of y dash of t. So I know the formula for Laplace of y dash of t. Replace it. So this gives me s times Laplace of y of t minus y of 0 plus the third term is no derivative involved. So keep it as such Laplace of y of t, which will be equal to, now what we have on the right hand side is e power minus t. And we know the formula for e power minus t as s plus 1. Since it is minus, it becomes plus. Coefficient a is 1. So it is s plus 1. Now what will be the next step? The next step, the first step we have applied Laplace on both sides. The second step will be apply what is given as your initial conditions. What are going to be my initial conditions? I have my initial conditions as y of 0 is 1 and y dash of 0 equal to 0. We will try to apply these two conditions over here. The first condition is y of 0 is 1. In your expression, find where you have y of 0. Here I have y of 0. The next term where you find y of 0, here you find y of 0. So what you do is you replace this y of 0 by the quantity 1. So this becomes s times of 1, so s, and this becomes a simple 1. What is the second boundary condition, as initial condition which has been given to us? We have been given y dash of 0 is 0. Where do we find y dash of 0? This is my y dash of 0. What happens to this value? This y dash of 0 is now replaced with 0. So when I replace with this with 0, this term entirely vanishes. Now I have applied the initial condition, which is going to be my second step. After applying the initial condition, I can simplify my expression. So what will be the simplified expression? It becomes s square Laplace of y of t minus s into 1 is s minus this has become 0. This becomes 3s Laplace of y of t minus into minus plus 3 plus 2 times Laplace of y of t equal to 1 divided by s plus 1. Now, let me collect Laplace of y of t to one side. So, what are its coefficients? S square over here, minus 3s over here, and 2 over here. So, these are my coefficients of Laplace of y of t. What are the left out quantity? Minus s plus 3. Take it to the opposite side. So, I will have it as 1 by s plus 1 minus s comes this side as plus s and plus 3 goes to the opposite side as minus 3. Let me take the LCM as s plus 1. So I will have 1 plus s minus 3 into s plus 1. Expanded 1 plus s into s is going to be s square minus 3s plus s makes it as minus 2s and minus 3 into 1 makes it as minus 3 divided by s plus 1. So I have Laplace of y of t into s square minus 3s plus 2 to be equal to s square minus 2s, 1 minus 3 is minus 2 divided by s plus 1. So we have this expression ready. Let us move to the next slide. So what will happen to my Laplace of y of t? What I can do is, I can cross multiply this quantity over here as coefficient to the denominator in the opposite side. So push it to the opposite side. So I will be left out with s square minus 2s minus 2 divided by s plus 1 into s square minus 3s plus 2. Now I know that this quantity s square minus 3s plus 2 is factorizable. So let me factorize the content as, what will be the factor? The product is going to be 2, sum is minus 3. I can split it as s minus 1 and s minus 2. Now this is my Laplace of y of t. Now what I want is to solve for this expression. So what I will do is, I will take this expression s square minus 2s minus 2 divided by s plus 1, s minus 1, s minus 2, and use any of the technique which I have known to solve for it. We know that partial fraction technique is going to be the easiest of all to get our answer. So I make this expression in partial fraction as a by s plus 1, b by s minus 1, c by s minus 2. I allocate three different variable constants for this because all the three factors over here are going to be different for me. So all the three constants are going to be different for me. Now let me take the LCM. So this will give me LCM is s plus 1, s minus 1, s minus 2. For s plus 1, what is missing? S minus 1 and minus 2. So this gives me a times of s minus 1, s minus 2. Next term, what is missing for s minus 1? Plus 1 and minus 2. So s plus 1, s minus 2 is attached to balance it. Plus c times of, what is missing for c? S minus 2 is here. So the missing quantity is s plus 1 and s minus 1. Now since the denominator of your first quantity and the denominator of the last quantity are the same, my numerators can be equated for. So this gives me s square minus 2s minus 2 is equal to a times s minus 1, s minus 2 plus b times s plus 1, s minus 2 plus c times s plus 1, s minus 1. Now our objective is to get the constants a, b, c. It is very easy since the factors are going to be simple for us. What you will have to do for the first factor? In the first factor, I will take s plus 1 to be equated to 0. When I equate s plus 1 to 0, what will happen? I will have s to be equal to minus 1. So what do we do is, put s is equal to minus 1 on both sides of the equation. So this becomes minus 1 the whole square. So it is 1. Minus 2 into minus 1. So plus 2. And this becomes minus 2. And right hand side now becomes, since it is minus 1, wherever I have s plus 1, that will become 0. So this will become 0. This term will become 0, leaving you with just the a coefficient, which is nothing but s takes the value minus 1, minus 1 minus 1 and minus 1 minus 2. Now over here on simplification, I have this to be equal to minus 2 and this is going to be equal to minus 3. Hence, a is nothing but 1 by 6. Hence, I have obtained the value for a. Now, what is going to be the next content? I want the value for b. How to get the value for b? I can get the value for b by equating s minus 1 to 0. So, what will happen? S will be taken as 1. So, you put s equal to 1 on both sides. So, it is 1 minus 2 minus 2 Since it is s minus 1 is 0, this s minus 1 will become 0. This s minus 1 will become 0. Hence, you will be just left out with b. And this s takes 1. So, it is 1 plus 1 and 1 minus 2. Leaving you with b value as 3 by 2. Next, for the last quantity, what will be our substitution for estimating C? Equate the last factor to 0. S minus 2 is 0, so S will be 2. When I put S equal to 2 on both sides, this becomes 2 square, which is 4, minus 2 into 2 minus 2. And this will be equated to S minus 2 is equated as 0. So this S minus 2 will become 0. This S minus 2 will become 0, leaving you with just C times of putting S as 2. So 2 plus 1 and 2 minus 1. Hence I get the value of C to be equal to minus 2 by 3. Now we are almost done with our values. The next stage will be resubstituting these values back in the partial fraction over here for A, B and C. Okay, so what will happen to this? I know this is nothing but Laplace of y of t. So in which case I have Laplace of y of t to be equal to the expression s square minus 2s minus 2 divided by s plus 1 s minus 1, s minus 2, which is a times of s plus 1 plus b times of s minus 1 plus c times of s minus 2. Now this gives me the value of a as 1 by 6 times of s plus 1 plus b's value as 3 by 2 times of s minus 1 plus c value as minus 2 by 3 times of s minus 2. Now this is nothing but Laplace of y of t. Now, we need to keep in mind what is our prime objective? To find y of t. Now, how to get my y of t back from my Laplace of y of t? So, what will I do in the last stage is apply inverse Laplace transforms on both sides. So, Laplace inverse of Laplace will give me back a y of t. What will happen to the right hand side now? This will become Laplace inverse of, because I am taking Laplace inverse on both sides. Okay, so when I take Laplace inverse on both sides, this will become Laplace inverse of 1 by 6 by s plus 1. Let me split it into separate values. Laplace inverse of 3 by 2 divided by s minus 1 plus Laplace inverse of minus 2 by 3 by s minus 2. Now, this is a simple quantity because we have already memorized the formulas for our basic functions of Laplace. 1 by 6 is a constant. Laplace inverse of 1 by s plus 1 is e power plus means minus t. Plus 3 by 2 is the constant. 1 by s minus 1. So, it is e power minus means plus t. Minus 2 by 3 is a constant. E to the power of minus 2 means it is plus 2t. Hence, I have arrived at the value of y of t, the solution of the given differential equation as 1 by 6 e power minus t plus 3 by 2 e power t minus 2 by 3 e power 2t, which is a combination of both your complementary function and a particular integral. So directly this becomes our general solution of the differential equation. That's it, children. So it's as simple like just go memorize the first two formulas. Apply Laplace on both sides. Apply the boundary condition in the next step. Solve for the quantities. Pick your coefficients. Go for a partial differential equation in your step 3. When you solve it using your partial fraction technique. So the partial fraction technique gives your answer for A, B and C. And at last, the fourth step will be applying Laplace inverse on both sides to retrieve back your y of t. Just as simple as that when you apply these four steps in order. Thank you.